So, welcome to this week's Origins Colloquium. We're very pleased to have Alex Lazarian giving us a talk this week. Alex received his PhD from the University of Cambridge at the Department of Applied Mathematics and Theoretical Physics, DAMPT, and then had brief spells at Harvard and in Austin, Texas, before taking a postdoctoral position at Princeton for 3 years. He was awarded a CETA fellowship, but only did 1 year of that before then moving with a faculty position to the University of Wisconsin-Madison, where he is a professor in the Department of Astronomy, but also affiliated to physics. And Alex has worked on a wide range of topics in theoretical astrophysics, particularly know his work on magnetic fields and turbulence, and I think we'll hear about that today. So welcome, Alex.
Okay, thank you very much. It's my pleasure to be at your colloquium. And as I see, we have very limited participation, so please feel free to interrupt me and ask questions, so we don't need to wait till the uh, you know, normal time. And I will spend some time talking probably of the trivial stuff that you all know about turbulence, but I did not know the audience, so therefore I thought that it was good to have this introductory slides, but I will be very fast of them. So in this talk, I will be talking about just a small focused aspect of MHD turbulence. Namely, I will be talking about SubAlfvenic turbulence and focus on the effects of driving. So it's something which was not clear for me, and I think it is not clear for most of the community that the properties of driving can significantly change the properties of turbulence. And the first slide shows the visualization of slices of data for velocity and magnetic field. And you see that velocity and magnetic field have a very different structure. So this is what is not expected in traditional MHD turbulence. And I would say that this is only happens when we have the velocity driving. However, velocity driving is the traditional driving for most of the interstellar simulations. These are my co-authors, my present student, Kawai Ho, my former student, Owen Kaho, and my long-term collaborator, Ethan Vishnak. Okay, turbulence is something which is scary, especially if you're in the plane, therefore fasten your seatbelt. What is peculiar about turbulence is that it is chaos. But if you look at this Leonardo's picture, you see that this chaos is not complete chaos. You see some order. And but this order is statistical order. Therefore, we can expect to have statistical description of turbulence. And the first statistical description of turbulence and the most influential description of turbulence was provided by Kolmogorov. And the idea of Kolmogorov theory is very simple. You have large eddies, and then these eddies decay due to nonlinear properties of hydrodynamic equations. And at the large scale, the effects of viscosity and therefore dissipation are negligible. So the energy is not dissipated, but it's going to smaller and smaller eddies. The characteristic time for the eddy evolution is cascading time, the scale of the eddy divided by the velocity of eddy. And the flow of energy from one scale to a smaller scale is, for incompressible fluid, is VL squared over T cascading, and it gives you the famous Kolmogorov relation. Note that Kolmogorov did not get this physical way, he got this mathematical way, but I'm mostly following this Richardson, formulation of turbulence. So we have a flow where we have at the large scale large Reynolds number. It goes to small eddies with lower Reynolds number, and it goes so on to the dissipation. Richardson suggested this, but he did not quantify it. He was writing this poem that you can easily read on the screen. And this is essentially the picture of turbulence, which corresponds to the Kolmogorov scaling. So you have some injection scale, a dissipation scale, but in the case of the astrophysical media, you also have an elephant in the room, and this is magnetic field, and which changes the nature of the motion. And for many decades, it was considered that the change of the nature of turbulence prevents us from using the notion of eddies. Well, nevertheless, interestingly enough, the cascades that we observe, for example, with electron density spectrum on your left, and also with the velocity on the multi-phase media, which was studied more recently. We see over many decades the same 5/3 spectrum, which is somehow suggesting that the nature of motions in MHD and hydro should be similar. In terms of the the applications are numerous, and you all know well that MHD turbulence affects most of the astrophysical processes. So, what is changing when we introduce magnetic field? We introduce some back reaction, which is characterized by alpha velocity. And when we have alpha velocity less than 1, we have SubAlfvenic situation. It's the situation where the magnetic field is very important, and when I will be this case that I will be talking about. In terms of the magnetic field lines, you see that the degree of stochasticity of magnetic field lines is changed as we change alpha and Mach number, which is a ratio of your injection velocity to the alpha velocity. If you have low alpha magnetic field, low alpha Mach number. In this case, you have nearly straight weakly perturbed magnetic field. That's what we will be talking about. So there are two regimes of turbulence in subalfvenic regime. And one regime is so-called weak regime that we introduced in our paper with Ethan, and then other, the most, renowned paper is Gautier next year. And then stroke regime, which is happening at smaller scales. A bit counterintuitive, but this is the case. So strong turbulence happens on small scales rather than on large scales. In any case, I will be focused on the weak regime of MHD turbulence. So a regime which is happening from the injection scale to the transitional scale. And transitional scale is smaller than the injection scale by the squared alpha Mach number. I remind you that alpha Mach number in our case is less than 1. So there are the MHD turbulence was studied by many people. Bill Matthews was an important driver of numerical study of MHD turbulence for years. And it was understood that MHD turbulence is important for many applications. On this picture, you see isocontours of velocity, and you see that there is a preferred direction, which is the direction of mean magnetic field. Well, for MHD turbulence, it is important to understand what's happening with magnetic field lines. And this is the picture of me young and also Ethan Vishniak young when we wrote our paper in 1999 on a connection of magnetic field in turbulent regime. What we found, well, first of all, I'm showing you this scaling of weak turbulence that we obtained in that paper. And the most important thing that we found there is that in turbulent regime, the connection happens within one eddy turnover time. So eddies are not constrained by the magnetic field in terms of their motion perpendicular to magnetic field lines. So this is extremely important. So all researchers before that thought that we are constrained by magnetic fields. Yes, we are constrained in terms of sending alpha waves along magnetic field lines. But if we are talking about mixing magnetic field lines, I'm sorry, in Zoom I cannot show my motions. Never mind. But you can imagine mixing of magnetic field perpendicular to the direction of magnetic field. So these are not constraints. And therefore we have eddies, and therefore we have also this Kolmogorov scaling and many other properties of MHD turbulence. So what do we have in terms of subalfvenic magnetic field? We have this K minus 2, and K, in this situation, we are talking about perpendicular scale. K perpendicular minus 2, it's weak MHD turbulence, and K perpendicular minus 5/3 and strong MHD turbulence at small scales. The thing for us to remember is that when we measure, as in observations, the direction averaged spectrum, in this case, in both weak and strong MHD case, we are dominated by the perpendicular motion. So therefore, we can see this minus 5/3 in the earlier slides, where there was no particular choice of direction of averaging. With my former student, Andrei Bezniak, in 2019, we published a book, Turbulence and Magnetohydrodynamics, and all different things that we know about turbulence, going much beyond what I'm going to talk. What I have told you is described there. So there was the motivation for this work. And our studies, which were done with magnetic driving, showed that magnetic energy and kinetic energy are in the equipartition. However, some of the studies, for example, Federath, Beatty, showed that magnetic energy is significantly smaller than kinetic energy in SubAlfvenic turbulence. The researchers attributed this to the compressibility effects. Well, but in other compressible MHD simulations, which were done by my collaborators, we also found that magnetic energy is equal to the kinetic energy. So what is going on? Is it indeed the compressibility, the culprit for this disparity? Or there is something different? Well, we know that compressibility was blamed for some effects earlier that later were found to be present in incompressible turbulence. And the most notable effect is the decay of MHD turbulence. When rapid decay, essentially large editon over time decay, was found in MHD turbulence, essentially everyone in the community decided that this is due to coupling between compressible and incompressible motions. But this was not true. And for example, we found in incompressible simulations with Jungehud shown that the decay is happening at the same rate that in incompressible case. Essentially, I will show in this case in my talk that the same is applicable for the case of disparity of kinetic and magnetic energy. It's happening in incompressible turbulence. And from now on, I will be discussing only incompressible case. So, how can we drive turbulence? In incompressible simulations, usually it's driven by so-called Alsasa variables. And it definitely gives, by definition of these Alsasa variables, the equipartition. But in ISM simulations, usually it's driven through velocity driving, and it's interesting to understand whether the velocity driving is the reason for the effect. So what's happening when we drive things in terms of velocity? In terms when we drive velocities, naturally we create a flow of fluid along magnetic field lines. And what's happening when we have a flow along magnetic field lines? Well, we have the so-called Bernoulli effect, which is related to the essentially conservation of energy. And if your velocity becomes larger, your pressure becomes smaller. And this is the effect that explains waves over the ocean. So you can expect that if you drive flow along magnetic field lines, you will expect formation of similar waves, but in magnetized turbulence. What does it mean in terms of the back reaction of magnetic field? Waves in the ocean do not get infinitely high because you have gravity. In the case of magnetic flux tubes with flow along them, magnetic fluctuations, compressions of magnetic field do not allow compensate for the pressure, and so the waves are limited by magnetic pressure. And it's very easy to see that the changes of magnetic pressure related to the intensity of the fluctuations or at the large scale, because at the large scale, the fluctuations are maximum. If we divide this part by B, we get something interesting, which says that the fluctuations, relative fluctuations of parallel magnetic field is not proportional to the relative fluctuation of the injection velocity, but it's proportional to this relative fluctuation of injection velocity squared. Delta B over B is usually identified also to the Alfvenic number. And delta and VL of VVA is identified with the Mach number. So what's going on? It means that we have, in terms of velocity, driving two different Mach numbers. And it also means that velocity fluctuations can be substantially larger than the magnetic field fluctuations. Just from this equation, you can see that you have this as essentially magnetic energy, this is kinetic energy, and this is Alfvenic number. So this is an interesting consequence of this exercise. Look, I did not mention compressibility of fluid at all. It's not relevant. Okay, so let's go further, and I will not torment you with this piece of from our paper, but just it's available publicly. You can read it and see that solenoidality condition of the magnetic field dictates to us that fluctuation in perpendicular direction should be of the order of the parallel direction. This is also not something which was my invention. It's been claimed experimentally by the researchers who are studying compressible turbulence. But for them, it was a mystery. Okay, so if we have delta B parallel of the order of B perpendicular, delta B perpendicular and delta B, so we can have the relation between this magnetic energy and kinetic energy without any problems, and we can see that this magnetic energy, which can be significantly smaller than kinetic energy if we have velocity driving. These are, again, the results which were obtained by Beatty, used by Skalidis and Tassis, and Skalidis had a very sophisticated explanation of this, but I don't think this is relevant. To show that the things are different for magnetic driving, we have this plot which clearly show that we have the equipartition between magnetic and kinetic energy if we get magnetically driven turbulence. So the effects that I was talking about, this disparity of kinetic and magnetic energy, is due to the nature of velocity driving of turbulence. Well, we did not stop on that. It would be really not right to stop when we found something new, so, because we found that essentially new regime of MHD turbulence, which I did not expect to have. And we studied also analytically and numerically the difference of scaling, and found, yes, kinetic energy follows K minus 2 as earlier in weak turbulence, as was suspected earlier, but magnetic fluctuation have a different spectrum, K minus 1. So this is by itself very interesting. And this spectra changing as we have for velocity driving, but we change alpha and Mach number. In this case, this spectra are changing, and when alpha and Mach number becomes of the order of 1, which corresponds to this delta B over B around 1, we have also equipartition between kinetic and magnetic energy. Incidentally, we found that in earlier work by my collaborator Santos Lima, the equipartition between kinetic and magnetic energy was achieved with velocity driving. But in this situation, we were studying intentionally the properties of weak turbulence, and we introduced anisotropic velocity driving, where we did not have this flows of velocity flows along magnetic field lines. And so it also resolves this puzzle, what was happening with Santos Lima et al. Well, we found also this, confirmed this theoretical prediction that there are two alpha and Mach numbers, magnetic and velocity Mach number. And this is the plot of the alpha Mach number in terms of velocity versus delta B over B. And the plot corresponds to the prediction delta B over B square root of. Well, what is very important, and this is what Jonathan asked me to mention, is that you can distinguish velocity and magnetically driven turbulence from observations. How? You can see this two plots. And in terms of what is shown here, this upper panels correspond to structure for, not, I'm sorry, this light row correspond to the structure function of magnetic field fluctuation as measured in synthetic observations. So these are 2D fluctuations of polarization directions, essentially. And the right column correspond to the structure function of velocity fluctuations. And you see that there is not much difference in terms of magnetically driven and velocity driven in terms of magnetic fluctuations. But there is a significant change of the properties in terms of centroids for magnetically and velocity-driven situations when we measure perpendicular and parallel to magnetic field. So it's easy to understand. If we have a lot of fluid motions parallel to magnetic field in a velocity-driven case, we definitely have more dispersion more difference between this parallel and perpendicular measurements. So this is just a test. But it's important that this can be used to study the turbulence in terms of the nature of its driving from observations. Well, another thing that we also found, actually first theoretically and then confirmed as it showed numerically, that in this weak regime there would be not only disparity between kinetic energy and magnetic energy, but it will be also a disparity between the alpha and slow modes. And there will be more energy in the slow modes, which has a lot of implications in terms of star formation, cosmic ray propagation, etc., etc. So there is scaling between alpha and slow modes related to alpha Mach number. So, well, in terms of the implications, there was known work which made a lot of impact by Skalidis and Tassis, and they were claiming that they must change the Davis-Chandrasekhar Fermi formula for the studies of magnetic fields from observations. And they attributed this to compressibility. We can say that for velocity driving, we have the same change of the Davis-Chandrasekhar Fermi formula, but it's not related to that compressibility. I also mentioned the implications in terms of heat and cosmic rays. It's natural. I will not dwell about this. Also, the driving of galactic winds and star formation can be affected by this velocity-driven SubAlfvenic turbulence. And it is important that it can be distinguished observationally. In our work with my co-authors, Pogosyan and Kaho Owen, we in fact suggested a universal formula for magnetic field studies. It involves the sonic Mach number and Alphen Mach number. In the case of velocity driving, it gets into the result suggested by Skalidis and Tassis. But in magnetically driving, it gets to the result original Chandrasekhar, Davis-Chandrasekhar Fermi formula. The advantage of this form of expression is that it can be applied to velocity channels, because for velocity channels we can find both Alphen Mach number and sonic Mach number. For example, by the gradient technique, but there are other also techniques which can be used for similar purpose. The summary is that for turbulence, for subalfvenic turbulence, the driving matters. And for velocity driving, we have new effects, which are fundamental, do not depend on compressibility. First of all, disparity between kinetic and alphenic energy. This disparity between slow and fast modes. We found a new scaling for the magnetic spectrum at subalfvenic weak regime. And we found that the changes of Davis Chandrasekhar Fermi formula, which was earlier attributed to compressibility, happens for incompressible turbulence. But for magnetic driving, we confirmed early results and that we have a similarity in terms of, or equipartition in terms of slow and Alphen modes, magnetic and kinetic energy, identity of velocity and magnetic spectra, and applicability of the traditional Davis-Chandrasekhar Fermi approach. And the important thing is that these types of driving are important by themselves, and they can be distinguished from observation. Thank you.
Thank you very much. So I have lots of questions, but we'll let people go first. So if you have a question, raise your hand in the Zoom, but perhaps Santiago in the Chalmers can help me coordinate. I can't quite see if you raise your hand there, so let me know if there's a question.
I have a question, but I don't find the raising hand
Oh,
anymore in
yeah,
Zoom.
they've changed it. Yes, Daniel, please.
Yeah. Hi, Alex.
Hello.
I had a very simple question. What is realistic, velocity driving or magnetic driving the ISM?
Well,
What?
you see, it's an interesting question, and I think it should be resolved observationally.
Hmm.
However, just my educated guess is velocity driving is more common.
Hmm. And
It's if you are talking about supernova driving or you definitely have velocity driving. At the
mm,
same time, magnetic-rotational instability may have the magnetic driving. At the same time, the counter argument to that magnetic rotational instability is not expected in the regime of a strong magnetic field. So again, it's
mm.
an interesting question, but we can analyze observations and answer it.
Well, maybe I
If
can
I may ask, or yeah, sorry.
go ahead, Daniel, and follow up on your question. Sorry, you go first.
If I may ask a very also simple question, how can I imagine the magnetic driving? Okay, you mentioned now already magnetic rotation instabilities. How else could I imagine it? I mean, velocity driving is, I think, intuitively clear. You add some acceleration to the gas, but magnetic driving is not so intuitive to me.
Oh, well, it's a good question. Well, potentially what you can do, you can have as it is done traditionally in in theoretical studies of MHD turbulence. There is an interaction of wave packets of or oppositely moving alpha wave packet create the higher perpendicular K. And potentially one can say, well, I'm talking from the top of my head. You have a streaming instability.
Mm.
Streaming instability creates alpha waves. These alpha waves reflect from density, well, discontinuity, the density contrast, and reflecting back. The interaction between the two creates turbulence, and this is, well, magnetic or
But
there's
practically,
such a variable you can driving. You can also think about reconnection. Reconnection also can drive turbulence, and it can also drive this magnetically. So,
but can I follow up
Okay.
on that? I mean, practically in a numerical simulation of turbulence for magnetic driving, would you simply be shaking the magnetic fields or injecting alphane waves without the velocity? Is that effectively it?
yeah. That's what we've done. That's what the simulation that I demonstrated to you.
Right, right. I mean, I wanted to ask about real situations in giant molecular clouds. One can also imagine different scales of the driving. So on a large scale, you mentioned supernovae, but you could have cloud collisions, which might work on large scales. And then, of course, you can have protostellar outflows, which would be, I guess, also velocity driving from small scales. Can you comment on how how we can distinguish that from your work here? Because so the injection scale.
Well, let me go back a bit. That's which may be relevant to answering your question. And this is, look at this velocity multi-phase spectrum. This is in the direction of torus molecular cloud. This is okay, I can say that this is a special case. But for, the 10 orders of magnitude, we have 5/3, and it's very important. There is no adjustment of the amplitude. These are amplitudes given by the essential whatever it comes from. It's the amplitude are real. And so if we believe this plot, in this case, we should conclude that the magnetic, the, molecular clouds are part of the turbulent ecosystem. And this ecosystem is driven on the large scale. So again, if we believe this result and if it is applicable to other direction, not only torus direction, in this case, we should not talk about small-scale driving as the major result for the formation of structures in the interstellar media. But, you know,
Right. I
the
agree with that.
same, pardon?
Taurus does not have a lot of star formation, so I wouldn't expect that to be the
Okay,
case.
fine. I'm not claiming this either, but for me, this was a really interesting result that we have this
Mhm. But I thought
universal
1333,
statement.
I thought NGC 1333 had been claimed evidence for small scale driving. I mean, maybe it's even a duo.
Oh, it would be very interesting in this case to use the same procedures that we use for torus. And this is and see whether we have a difference. Okay,
Mhm.
let's assume that we have small scale driving. Well, if we have small-scale driving, the question is this subalfvenic or superalfvenic? If this is superalfvenic, in this situation, we should have the the case, and I will show you this plots because usually, theory is not believed by, okay, just a moment, but numerics are believed. So this is, look, this is the case of delta B over B is 1, the rightmost panel.
Mhm.
And in this case, there is no effect of subalfvenic turbulence that I was talking about. And therefore, for such a cloud, you should apply your Davis gradient. You know, I was working on grain alignment, and therefore, when Davis is associated with me with
Yes.
Greenstein, but
Yeah.
this is Davis Chandrasekhar Fermi technique. You apply Davis-Chandrasekhar Fermi technique if you can apply it to superalfvenic clouds, which I strongly doubt.
Hmm.
So there is no disparity, at least, between kinetic energy and magnetic energy in this
Did
case.
anyone else want to comment on the small scale versus large scale driving before we go to Brandt, or is
Yeah, I just want to comment. And hi,
okay, please.
Alex, long time. Yeah, so I mean, going back to what you said about protostar jets, I mean, jets can both do driving both through velocity, just because you're injecting velocity into the region, but they can also pluck the magnetic field lines, and the Alfvén speeds in this case are generally quite a bit higher than the gas speeds. So one could imagine that if you looked at, say, two chemical tracers with similar critical densities, one is an ion, one is a neutral, that as you kind of go further away from the protostar, one might see a different signal of the turbulence. Is basically the ions are responding to the magnetic fields, but not the neutrals.
Well, it's really a new avenue for studies. We should definitely use numerical simulations, and I know that your group has very much advanced simulations, and go ahead with that.
Okay, great. Any other questions for Alex? Yes, Gina.
Question about the observability. Can you go back to your plot of the observational comparison?
Uh, Again, I did not hear the first words you said.
So can you go back to the plot with the observational prediction?
Uh, uh, Observational. Okay. Okay, yes.
Yeah, so there, should we be looking for a different slope between the two velocity power spectra or a different?
The, um, well, it is there's a moment I see the size, the big, the dispersion between the parallel and perpendicular structure functions. Slope, we do not see any significant change, but so this dispersion. In any case, what I suggest, you see, this is very preliminary. I never try to do this very carefully and quantify this. This just shows that there is a difference, and this difference observable. By making more extensive simulations, you can have the table, how much you expect the difference for different driving. And if we have, as was suggested also, this mixed driving, what it also involves.
Yeah, that would be interesting. Thank you.
Okay, any other questions for Alex? You mentioned, Alex, the implications for star formation, and perhaps you could elaborate a little bit more there.
Oh, yeah. Happy to do that. Let me see which is which.
I suppose.
Yeah, here, example, yeah. So, in but there are different ideas about the nature of molecular clouds. But they can be also associated if we're talking from looking from the point of view of theory of turbulence with the compressible part of MHD cascade. And in the compressible part of MHD cascade, we have the slow modes, which can compress the media. And the fact that we can have more energy in the slow modes compared to Alphen modes, I think is interesting and has implications for star formation.
Well, there's been, as you know, these long-standing questions about what is maintaining turbulence in clouds. So do you
Well, again, if I'm sorry, I caught your question very fast because I heard a lot of discussions of this theme. Yeah, it's a very important question. What is the nature of the molecular clouds, whether they need to be supported or whether they need to have internal or external driving. But again, in this case of non-star forming region of torus, if they're a part of the cascade and we do not see much change of the spectral slope for the turbulence in that direction in different species, well, it's the cascade is going, and the energy is coming from the larger scales to the smaller scales. This is just
Well, we,
Kolmogorov.
we need more clouds. I mean, Taurus is not particularly
I
typical.
understand, but let me be provocative, and there are specialists who can do both numerical simulations and the comparison with observations.
Mm,
And this is how we can resolve this question. It may
mm,
be not one answer. It may depend, and we may find some peculiar features. The
mhm,
issue is that we need to use proper techniques to study this, because, for example, usually use centroids have a lot of problems because they are dominated by density, and therefore, if I were showing the same plot in the direction of torus, well, not star forming.
mm,
Using centroids, I would have a lot of amplitude changes, and the natural quote unquote explanation would be yes, there are these internal sources of turbulence and molecular clouds.
mm,
But if you use pure velocities, which are a better measure of statistics of turbulence, in this case, we don't see it.
mm,
So.
mhm. We're going to have to finish soon, but let me ask one last quick question about the evolution of the mass to flux ratio and reconnection diffusion. And as you know, when we form stars, we have to lose a lot of magnetic flux. And reconnection diffusion seems like a good way to do it. But perhaps you can comment on the rate of that process in subalfvenic turbulence.
Well, actually, it's a very good question, and this allows me to advertise the, well, I'm trying to find this Santa Slima work, which exactly was devoted for the study of the a connection diffusion in subalfvenic turbulence, and it's found to correspond to the theoretical prediction, which scales as, if I remember correctly, it has the small factor of MA squared or MA third. I forgot, I'm sorry. But there is this factor of decrease compared to the strong turbulence where it's everything is happening with an eddy turnover time. So it has some extension.
Well, we can check the paper. Great.
Yeah.
Any last comments or questions for Alex before we finish? Well, I'm going to stop the recording, so let me do.
Just a general quick comment is that what we showed a few years ago was that reconnection diffusion itself can possibly sustain enough cosmic ray acceleration to reproduce observations. So it could be that there's a bit of kind of a self answer here, but this assumes some scalings that might, not be valid anymore, but probably close. So
Yeah. Well, you're right. That's another important implication. Very good. Well, let's thank Alex again.
Hey, thank you very much for your